Hey everyone, and welcome to today's Explainer. We are going to explore the hidden, highly tactile forces that allow our physical world to literally bounce back. We're talking about the physics of resilience, the invisible rules that dictate how materials handle stress, bend to our will, and then miraculously snap back to exactly how they were. It's an incredibly elegant mechanical property, and it's hiding in plain sight in almost everything you touch. So let's just dive right in and uncover the mechanics behind elasticity.
Section 1. The Magic of Bouncing Back.
I want you to visualize something for me right now. Have you ever stretched a rubber band, feeling that increasing tension building up between your fingers, and then watched it effortlessly return to its original shape the exact second you let go? Or maybe you've compressed a metal spring just to feel it actively fighting to push back against your hand. It's a deeply satisfying tactile sensation, right? Well, that resistance, that immediate and perfect snapback, that isn't just magic. It's a very specific property of physics in action. Which brings us to the formal definition. Elasticity is the property of a material that allows it to return to its original shape and size after a deforming force is removed. So the crucial takeaway here is that when a force is applied, like your fingers pulling on that rubber band, the material actually changes shape at the molecular level. Its internal bonds are stretching to accommodate the tension. But the very instant that deforming force goes away, the material perfectly regains its original form. It's literally the ultimate physical reset button. But as with all mechanical laws, there are some pretty strict boundaries. Let's see how this builds.
Section 2. Hooke's Law and Limits. Now, every hero needs a good antagonist, and in the story of elasticity, that antagonist is the elastic limit. We're really looking at two very different states of being here. When you are below the elastic limit, you're in the safe zone. The material safely returns to its original shape because its molecular bonds are just stretching, they aren't breaking. But if you push too hard, you enter the dreaded above elastic limit zone. Here, if the applied force exceeds what the material can physically handle, it becomes permanently deformed. The internal structure literally slips and rearranges itself. Actually, scratch that. It doesn't just rearrange, it breaks its fundamental structure, meaning it will never bounce back to its original state again. It's the physical danger of pushing something entirely beyond its natural breaking point.
But hey, as long as we respect those boundaries, we are governed by an absolutely brilliant golden rule. Hooke's law states, within the elastic limit, the extension of a spring is directly proportional to the applied force. That word right there, proportional, is the absolute key to the whole shebang. If you pull a spring with a certain amount of gradual, increasing force, it stretches. If you double that force, it stretches exactly twice as much. This perfect linear mathematical relationship between force and extension is exactly why this matters so much to engineers. Predictability allows for design, Because we know precisely how a material will behave under specific loads, we can engineer complex structures that intentionally bend without ever coming close to breaking. Section 3. Elasticity in everyday life. So what's really fascinating is the sheer massive scope of where elasticity is used to build a safe, durable, and frankly really fun world around us. Just think about transportation. Engineers harness this predictability to use elastic materials in vehicle suspension systems, absorbing those violent shocks from the road so you don't feel them. They use them in bridge expansion joints to allow massive, heavy steel structures to flex safely under the extreme weight of traffic and changing temperatures. Then you've got everyday objects. We see springs meticulously regulating the precise timing in mechanical clocks and providing highly calibrated measuring resistance and weighing machines. And of course, sports. The breathtaking heights of trampolines, the massive snap of diving boards, and the literal life-saving stretch of elastic ropes all rely entirely on the exact mathematical relationships we just unpacked. The stuff is literally everywhere.
Section 4. Summary and Final Thoughts.
Okay, to really lock in our understanding, let's walk through the exact step-by-step cycle of elasticity. Step 1. Apply force to deform the material. You are actively putting energy into the system. Step 2, and pay attention because this is absolutely the most critical part of the process, remove that force before exceeding the material's elastic limit. Step 3. Watch as the material smoothly regains its original shape, releasing that stored energy and doing so in perfect proportion to the force that was applied. This simple three-step dance is exactly how everyday materials handle immense stress without ever failing. It really is a wildly fascinating physical property, and honestly, it offers quite a profound metaphor. We've seen how materials can endure stress, stretch to accommodate heavy applied forces, and then bounce right back entirely unscathed, provided they don't get pushed past their ultimate limit.
So, I'm going to leave you with this final thought as we wrap up today's explainer. Now that you know the hard and fast rules of elasticity, what limits are you stretching in your everyday life? Thank you so much for exploring the physics of resilience with me, and I highly encourage you to keep questioning all the invisible forces that shape our world.